Welcome. One of the things you will quickly discover about statistics is that we have thousands of ways of doing the same thing. In fact, we've already seen hints of this along the way. For example, we've already seen that there is more than one definition available for the mode of a dataset. For example, the mode could be defined as the most frequently occurring data value in your dataset, or it could be the midpoint of the most frequently occurring class in a GFDT for the dataset. This means that if we structure the GFDT differently, you could actually obtain a different mode from the other GFDT. Here is a small toy dataset presented as a stem and leaf plot. As is highlighted here, the mode is 31, the only value in this dataset of whole numbers to occur 3 or more times. However, if we represent this dataset as a GFDT with class width 5, shown here as a tally plot, the mode would be the midpoint of the most frequently occurring class, which is 10 to 14. Thus, the mode using this definition would be 12, which is different from the original mode of 31, and we also note that there actually is no value in the dataset that equals 12, thus there is no data value equaling the mode. And if we reconstruct the GFDT using a class width of 10, we get a different modal class, 20 to 29, and thus a mode of 24.5, which differs from the other two modes, is not a data value in the dataset, and is not even a number that could be a data value in this dataset, as the data consists of whole numbers only, and this value has a fractional part of 1/2. This is an example where different definitions for the same general concept, in other words, most frequently occurring, results in different or even contradictory values. Let's revisit the idea of the GFDT to examine this concept further. Here we have another toy dataset presented using an expanded stem and leaf plot. If we convert this to its parallel GFDT, that is, a GFDT with a class width of 5, we see something of a multimodal distribution. This is most clear using a tally plot representation for the GFDT, where we see two major modes at the extreme ends of the distribution and a possible minor mode in the center. However, if we were to present the data using a GFDT with a class width of 10, we end up with a different shape for the distribution. In this case, it appears to be a uniform distribution, with each class having the same frequency. Again, doing the same thing in a slightly different manner appears to produce different results. You may recall that another feature that may differ from one GFDT to another for the same dataset is the first lower class limit. Using this toy dataset presented in a stem and leaf plot, if we build the corresponding parallel GFDT, in other words, using the same class boundaries as suggested by the stem and leaf plot, we see a distribution with a mild skew. However, as some may not prefer the upper class to have only one actual value, the class from 100 to 109 can only have perfect scores of 100%, it is possible, and possibly more appropriate, to reconstruct this GFDT using an initial lower class limit of 51. So the first class is not 60 to 69, but 51 to 60. Thus, the last class is not 100 to 109, but 91 to 100. In this slight variation, the tally plot for this GFDT seems to suggest a much stronger skew in the distribution. Again, doing the same thing in a slightly different fashion appears to tell a slightly different story. Some may ask which way is correct, and the truth is that there is no definitive answer to such a question. The different approaches might be appropriate in different contexts. Or it may just be a preferential choice for which you prefer to best convey the story you wish to tell using your data. Sometimes the variations are pragmatic, such as the difference between stem and leaf plots. For example, we already know about the difference between a regular stem and leaf plot and two natural variations. The first is the expanded stem and leaf plot, which splits each stem into two separate stems. This plot does not require any new notational elements, but it does require the reader to understand the interpretation of two stems with the same labels. For example, the first 1 pound stem is for the data values from 10 to 14, and the second 1 pound stem is for the data from 15 to 19. Alternatively, we could go in the other direction and present the data as a condensed stem and leaf plot. As shown here, this does require a new notational element, namely the asterisk to indicate the separation between the two stems that have been combined here into one. The purpose and benefits of these variations are rather obvious. But even here, there is still a variety of ways that the same thing can be accomplished in different ways. For example, this condensed stem and leaf plot is not the only possible quote-unquote correct presentation. Here is the same data in a different condensed stem and leaf. Whereas in the first stem and leaf plot, the 10s and 20s were combined into one stem, and the 30s and 40s were combined into the other, in our revised condensed stem and leaf plot, we have combined the 20s and 30s into one stem, thus leaving the 10s in a stem for the aughts and 10s, and the 40s in a stem for the 40s and 50s. Again, neither is correct or incorrect. They are just possible variations that are available to use. As another example which has specific applications in different scenarios, we can look at a common measure of spread. For the standard deviation, we've seen two different formulae, one for the standard deviation for a sample, and a different formula for the standard deviation for a population. Here, the context suggests why we might want one over the other, but the key point is that there is more than one way to obtain the quote-unquote standard deviation. And this happens again and again in statistics. Other times, there is not a contextual clue suggesting which approach should or should not be used. And when first encountering this in statistics, it can be frustrating and daunting. But there are times when it works well to have variability in the types of analyses or protocols you might choose to use. There also is a historical reason behind this. Statistics, as an academic discipline, is relatively new. In fact, it essentially has only been around for under 150 years, and that even may be a generous estimate for the actual age of the discipline. There were seeds of statistics that had started to form going as far back as 400 to 500 years, but as the discipline we now understand it to be, it is relatively young. Part of this is because the discipline evolved as people were applying the techniques they were creating or discovering to the domains in which they were doing practical work. Whereas mathematics evolved a firm foundation and spread from that foundation, like ivy growing along the forest floor, statistics came into existence in more of a popcorn-like fashion, as it was used in a variety of disciplines over time. It popped up in other disciplines, like chemistry, agriculture, economics, and psychology, and it wasn't until researchers in those disciplines started talking to each other that people realized, hey, what you just described as that technique is probably the same thing that I've been doing over here, and I've been calling it this technique. So as a consequence, we quickly ended up with lots of different terminology, lots of different variations on algorithms, and lots of different notational systems. Alas, since it is so common in all academic disciplines to hear researchers say, oh my goodness, your notation and approach is so much better than mine, and I think we should abandon the way we've been doing it for the last 15 years and start doing it the way you're doing it instead. That way, we're all on the same page, he typed with unabashed sarcasm. Of course, this is not how things work in the real world with real academics and very real egos. The economists came up with their techniques, and they thought they were great. The engineers came up with their techniques, which they firmly thought were far superior to anything the economists ever did, and so on. And then we add the mathematicians to the mix when statistics became a viable topic of research in mathematical science, and even more notations and complexities were introduced into the growing cacophony. The moral was that no one discipline was really willing to change to match any of the other disciplines, and as a consequence, we end up seeing this myriad of conventions, notations, and approaches to data analysis that have been used in the different disciplines. And thus, we find ourselves here in this current situation of having thousands of ways to do the same thing. And here's one of the places where having more than one approach actually proves beneficial in the long run. And this is how we summarize and report info about a data set. We've already seen how to do things like measure center and spread, calculate the relative position of a data point in a data set, classify possible outliers in the data set, and provide overall descriptions for the density of the distribution. But recall, for these measures of center, spread, and position, for the general shape and possible presence of outliers, if we have a nearly normal data set or nearly normal distribution, then we can use the mean, in particular the arithmetic mean, for the measure of center. Correspondingly, we could then use the standard deviation to summarize the measure of spread. Taken together, we can calculate the z-score of a data value to describe its relative position. Then, if the magnitude of the z-score is greater than 2, we can consider that value to be a potential outlier. And finally, to better understand the overall shape, spread, and general density of the distribution, we can use the count by thirds empirical rule. But we must stress that this approach is ideal or only applies to the normal distribution or nearly normal distributions. It is not that we can't calculate these things if the data is not normal, but the overall interpretation may be hindered, and for the count by thirds empirical rule, the rule simply won't hold for non-normal data. So what do we do when we have non-normal data? Well, what we will do is introduce here a number of alternative strategies to calculate the exact same concepts. Again, this is 1,000 different ways to do the same thing in statistics. For example, to measure the center of the data set, we will now use the median instead of the mean. We will introduce the IQR, the inner quartile range, to measure the spread of the data in place of the standard deviation. And to measure relative position, we will talk about things called percentiles. For outliers, we will introduce a new rule called the 1.5 IQR-rule, and we will talk more about this shortly. And lastly, to talk about shape and density of the data distribution, we will use something called the 5-number summary and its graphical counterpart, the box plot. The advantage for this new set of techniques is that it does not require the data set or the distribution to be normal or bell-shaped. In the next video, we will explore these new approaches further, starting with the median and the percentiles.